Hi Dr. Zhang, this is Matthew Kahn from ECE5701 doing my Project 1 presentation on cell phone carrier signal to interference ratio simulations. And I'll just go ahead and first describe my code to you and then get into the simulation results. So first of all, the first thing I did with the code was to extrapolate from one quadrant to all four quadrants, completing the hexagon of receivers. So to do that, I had to multiply m and n by 2 and add 1. And that quadrupled the total area of which completed the hexagon. And I added variables for each of the different neighboring base stations using the same frequency. I added a sum of the interferences, and I added a C to I array for that result. I also had to add in a few more lines to be considered for the upper bound and lower bound for the y coordinate for the hexagon receiver locations. And then after that I had to include the equations for determining the distance for each of the interfering base stations, which I added my own distance function down here. It's just a simple Pythagorean theorem, and then I use that distance in each of these interference calculations for the interfering base stations. After I calculate the interferences, I convert them each to linear and sum them up, convert it back to decibels. Then I calculate the C to I ratio, which is simply the CP minus the sum of the interferences. I calculate the total number of receiver locations, and then I calculate the total number of receiver locations which had a C to I ratio that exceeded the threshold specified in the project requirements. I then calculate the coverage, which is the total number of locations covered divided by the total number of locations, and I print that. You can see down here my last simulation output is I've commented out the outputs for the C, and so I've just included the output for the coverage percentage. And so while I was determining my simulation results, I simply varied each of these sigma, which is the Gaussian variable shadowing effect, and n, which is the path loss index, and r, which is the radius of a hexagon from center to corner. And so I'll just do an example simulation here. If I run this, you'll see that I get a satisfactory display of a hexagon. You can see that the receiver or the carrier signal strength is highest near the center where the home station is located, and falls off as you move away from the home station. And so I'll move on to show you my simulation results. This table has my simulation results for 3 different values of R, sigma, and n. And then on the right column I have the percentage of coverage where the C to I ratio exceeds the threshold. And for my simulation variables, I've selected each of the boundary values, as well as one that's located in the middle of the boundaries. For example, the radius I used 1, 5, and 10. For sigma I used the values 3, 6, and 8 dB. And for the values of the path loss index, I used 2.5, 3.5, and 4.5. And so I noticed as I increased the radius of a hexagon, it did not significantly affect the total coverage, which makes sense within this simulation. But I believe if we took noise into consideration, that increasing the radius to very large values would leave some regions which did not receive a carrier signal that could overcome noise in the environment and in the electrical circuitry. But it makes sense within this simulation because we don't consider noise. Then sigma, I noticed as I increased the value of sigma that the output coverage, or the total coverage, would be reduced significantly. And this makes sense because as you increase the variance caused by shadowing, you'll get more and more locations which fall below the threshold. You have a greater chance of a location being dropped below the necessary strength in order to achieve the coverage threshold. So that makes sense. I noticed that as I increased the value of the path loss index n, that the C to I ratio increased. At first this confused me because I thought that the signal loss would weaken the signal, which it does, but it also weakens the interference signals. And because the distance from the receiver to the home station is smaller than the distance from the receiver to one of the closest 6 interfering base stations, the effect of path loss on the interfering signals is significantly greater than the effect of path loss on the carrier signal. This results in a smaller value of C, but a significantly smaller still value of I. So your overall ratio will increase as the path loss index increases. Again, this makes sense in this simulation, but because this simulation does not take noise into account, I would expect that if noise were taken into account, that a significantly high value of n would cause enough path loss that certain regions near the outer edge of the hexagon would experience too much path loss to the point that their signal would not be able to overcome environmental noise, and you would not receive a satisfactory coverage. In reality, that is. But again, in the case of this simulation, it makes sense. And so those are my results. They make sense to me, and I learned a lot from this project, and thank you for your time, Dr. Singh.